Delayed start. So, we are starting a new unit. Now, this information goes along with what we learned, but I think it reinforces what we learned in a really positive way. So let's get these notes out. Let's see. Quizzes are kind of graded. I've graded the first page of the quiz and all my classes, and then my fifth period, I got the second page graded already. So probably by tomorrow, by this period tomorrow, I'll probably have them all graded, and which is good. It was good, and you? Okay. So everyone has a sheet, note sheet. Armin, did you get one? All right. Exponential functions. Let's see how we do. Let's go. All right, ready? Yes, I'm still playing my target game. Doing really well this time. You can get the high score. Yeah, we don't judge. Okay. Here you go. Yep. All right, so exponential functions. So let's talk about where you would see exponential functions, and let's talk about where you won't see exponential functions. Exponential functions have growth. They also have something called decay. Growth means there's getting more and more, and decay means there's getting less and less and less. Make sense? Places where exponential growth. Well, let's talk about the big obvious one. As soon as Jake puts his phone away, that everyone knows. Bitcoin. Bitcoin. Has it grown?
Yeah.
Now you hear people going, dude, if you had invested $10,000 like a year ago, you'd be worth $45 million right now. I'm just hypothetical saying, but you have an earbud in. So Bitcoin has grown from a certain value and it's gone to a higher value. Now, I will tell you how life of investments works is this. Some people get on something that's hot in the beginning and they make money off of it. Some people think, I have the next best idea of what I'm going to invest in, and unfortunately they lose everything, right? So when people say, oh man, you're stupid, you didn't invest in Bitcoin. Okay, I kind of take offense to that because, one, I'm not sitting there watching the market and hearing about something a year after the fact. Why would you say someone was stupid for not investing in something because something happened over a year made it worth something really quickly when someone who was not involved in following the market? That doesn't make sense to me. So, in my opinion, as far as investments go, if you will get to a point in your life where you will perhaps try to save some money. What is a fantastic way to save money? Don't spend it. That's the one. But is there a get-rich-quick ideal thing? Absolutely. There are things called penny stocks, which are pretty much worth pennies. And you hope to, by investing in these penny stocks, that these penny stocks no longer become penny stocks. You hope they become dollar stocks, and $10 stocks, and $100 stocks. But there's a lot of things out there that are penny stocks that are never worth more than a penny. They're worthless. So my father is a prime example of this. My dad is the guy that you will meet one day and you probably physically won't meet my actual father, but you will meet people like my father who they have a friend that. You ever hear those stories? I have a friend that. everybody has a friend that, hey, how are you? Wow. Cool. All right. Everyone has a friend that beat the odds on something, right? I have a friend that ate 15 Big Macs in one sitting at McDonald's. Okay? You know, what does that have to do with investments? I have nothing. Everyone has a friend that somehow beat the odds. Then you have the one-upper. You guys don't know what the one-upper is? What do you got?
Where it's like you say something that you get good at, and then your friend's like, oh, but I did this.
Yeah, they're trying to one-up you. And there's a comedian I enjoy. His name's Brian Regan. And he had a little spiel about talking about the one-uppers as well. And he said, he goes, the funny thing is, what if you were at dinner or some dinner engagement or some social engagement, and you have everyone talking about and they're one-upping each other, and then here comes in Neil Armstrong who walked on the moon. How can you one-up him? You know, it's like, hey, I flew this jet really fast. I walked on the moon. You win. So, I don't know. So it's just kind of those kinds of things. So, exponential growth doesn't always continue on an upward spiral. It's something that eventually turns into something called the logistical model, which means it tapers off and stays at a certain level. So it doesn't keep going. Now, I will tell you right now, we have an exponential growth problem taking place. It is starting to taper off, but it's still catastrophic. And it's the flu epidemic. Okay? It's, you know, what's the best medical advice out there? I will tell you it's not the news. I will tell you it's not something you read on the internet. It's actually listening to the knowledge of a doctor. But people say, oh, because people didn't get the flu vaccine, this is going bad. Well, how the flu vaccine works is the Centers of Disease Control looks at the southern region, which just got done with winter, and you know they're opposite seasons from us. So they're actually, as we're kind of progressing out of winters, getting into spring, they're coming out of summer, going into fall. You know, like Australia and South America and stuff like that. So they recognize, okay, what kind of flus took place, and what's the probability. Now, you can't give a flu vaccine to somebody with all of the flu strains in it, not because you're going to harm the person, but it's too expensive. It's too expensive to take I'm just going to have a hypothetical number, but let's say there's 500 different types of strains of the flu. It's too expensive to put all 500 strains of the type of flu into a vaccine to a person to build their immunity so they don't get the flu. So what they do is the Center of Disease Control looks at these are the types of flus that had shown themselves this past winter in the southern hemisphere. Okay, so we saw, you know, let's say 10,000 cases of type A and 5,000 cases of type B, and then I saw like 45 cases of C and 12 of D and things like that. And this is just measured by in the hospital. So what they're going to do is they're going to take the top 2 or 3 and say these are our highest probability of these hitting the United States. They put those top 2 or 3 into a vaccine, and you get the vaccine, and your body recognizes, oh, if this comes along, I've already built the white blood cells to say, flu, you ain't coming in. And then every now and then, that low flu vaccine, or that low flu, where there might have been a couple hundred people that got it in the southern hemisphere, that might have been the one that really gets exploited. And you all might be too young for this, but you might remember there was, I think it was in 2012, there was a swine flu that came through, and man, it was nasty. And it really threw a lot of kids for a loop and society for a loop. So what happens is, you know, somebody comes to school and they ache and they have a fever and they're exposing everybody to their flu that they have. Will everybody get it? No. Will more people get it than probably should have? Yes. So when you're aching and you have a fever, guess what? Stay home. And don't fall under the assumption of, I don't have a fever anymore because I just took aspirin or Tylenol or ibuprofen. you still have the things going on in your body too that are catchy. But so the basic rule is if you have a fever, if you have not taken anything to reduce your fever, you should not be exposed to people for at least 24 hours after your fever is gone. And that's the best way to prevent spread of those types of diseases. And a lot of times that's colds or flus. Okay, but let's go into a little bit more. So we've worked with lines, straight lines, and we know that straight lines, they can cross the x-axis, they can cross the y-axis, they can be vertical, they can be horizontal, they can have negative slopes, they can have positive slopes. So determine the equation that represents a linear function. Well, I feel pretty darn comfortable saying that's a linear function. That looks like y equals mx plus b, right? That crosses the y-axis at 0, 1, has a slope of 1 because in front of the x is a 1. I also feel comfortable that this is a linear function, and that crosses the y-axis at 1. It has a slope of negative half. I also feel comfortable that this is a linear function because that crosses the y-axis at 0, negative 3, and it has a slope of 1 over 2. But the other three, problem number 1, problem number 2, and problem number 4, are not linear functions. This is a square root function, so this kind of graph looks like this. That doesn't look like a straight line. Okay, notice I only have an arrow at one end, so it starts someplace and keeps going. This one is a third degree polynomial, so it looks like this. Okay, and then this is a parabola, so it looks like this. Okay, so those are definitely not linear functions, honey. No, they're not straight lines. Okay? May I move to the next board? Is there anything that I'm not hitting well enough? All right. Exponential functions. So we just basically talked a little bit about it. So things that grow or things that don't or decay. So what do exponential functions look like? And what are some of the characteristics of exponential function? Okay, so I'm not going to draw the xy axis, but an exponential function can look like this. Okay? It can also look like this. Notice the arrows point in both directions. It can also look like this. And it can also look like this. Those are all exponential functions. Now, some of those are growth and some of those are decay. That's what your graph of an exponential function looks like. It will go forever left and right, so the domain of an exponential function is, for the most part, going to be negative to positive infinity as far as this class goes. Okay, so I'll write that, and maybe we'll focus on that, and maybe we won't. So the domain of exponential functions for at least this class right now will go from negative to positive infinity. The range we'll talk a little bit more about in a little bit. Okay? Everything seem okay? All right, so you have a starting point. So you have y equals a times b, and b happens to be raised to the x power. So you have your variables. Okay, so the starting point. So things that you need to, they tell us our growth rate is b. Okay, and we'll talk a little bit to know when that's growth or decay. Our starting point is at a. So if you were to start a table, and you could have some negative numbers in there, you could have some positives, you could have 0. The one that I feel most comfortable with is a times b to the 0. And a and b will represent numbers of some sort. We just have them represent variables. We just got done with a quiz, and I saw that a few of you got this type of problem correct. But if I had b raised to the 0 power, what is the answer? 1. So if I raise something to the 0, so you didn't get it right. All right, so a times b to the 0 power is the same thing as a times 1. So that gives me 0, comma a. So 0, comma the value that is not raised to an exponent will be where it crosses our y-intercept. Okay, remember that's our vertical, so it's a dot, 0, comma a. It could be positive, negative, it could be 0. Good so far? I'm not going to fill out the rest of that because I don't know what A and B are at this point. Well, let's see if we can play around this. Okay. So we're going to fill in this table. And we want to see which one would be exponential, which one would be linear. I'll tell you the one on the left side is exponential. How do I know? Because I have an exponent that's x. The other one's linear because that's set up as y equals mx plus b, where they just taken mx plus b and they flip-flopped it. So if I were to take 0 and plug it in, 2 raised to the 0 power is 1. 2 to the 0 is 1. So I get 16 times 1 is 16. Okay, if I plug 1 in, 2 to the first power is 2. What's 2 times 16? If I plug 2 in, I get 2 to the second power, which is 4. 4 times 16 is 64. Okay, plug 3 in. 2 to the third is 2 times 2 times 2 is 8. 8 times 16 is, I don't know. Anyone have a calculator? Can't do it in my head. 128, you think? 128? Love you guys. 128. 2 to the fourth. 2 times 2 times 2 times 2. That's going to be 16 times 256. Holy cow. And then 2 to the fifth. That's 32 times 16. So I believe it's 512. How do we feel about that? So if it was linear, we would have the same distance. So from here to here, it's 16. Oh, we're on a good start. From here to here is 32. From here to here is 64. From here to here is 128. From here to here is 256. So it's definitely not linear because we don't have the same distance. We're counting at the same increments in x, but our increments of y are stretching out a lot more. So again, if I plug into this first one, 2 times 0 is 0, plus 16 is 16. 2 times 1 is 2. Add that to 16, I get to 18. 2 times 2 is 4. Add that to 16, I get to 20. 2 times 3 is 6. Add that to 16, I get to 22. 2 times 4 is 8. Add that to 16, I get to 24. 2 times 5 is 10. That becomes 26. Notice, each of these is 2, 2, 2, 2, 2. And as I said, each of these, that goes from 16, that goes to add 32, you add 64, you add 128, you add 256. So the growth factor of this goes a lot faster than the growth factor of this. The growth factor of this is constant. It's just a straight line if I graphed it.
Would that first chart, would the graph be like flat and then rise?
It would look like this, like that. There would be an XY axis normally there. I'm just trying to give you a visual of what it would look like. Everyone happy so far?
Yeah.
Sweet. Let's see. This one. All right. Oh, we just talked about these. Okay, so you have when your blue, when A is greater than 0. So when this is a number that's larger than 0, and your B value is bigger than 1, so that's 2, 3, 4, 5, 6, 7, you grow like this. When your A value is less than 0, so when that's negative, but your B value is doing that. Okay? So as you looked at that first set of graphs, let's just put a circle around it so we understand what we're talking about. When we first look at this, as I go to the right, so as I go out this way, does it appear that our line is going away from the x-axis, or is it coming to the x-axis as I go further to the right? It's going away. So this is definitely going away, and this is going away. Okay? So let's look at this next one. When A is greater than 0, so look at this, but then I have a fraction. I have between 0 and 1, or a decimal. Between 0 and 1, this is coming to the x-axis as I go this way. Agree? So these are growth, and these are decay. So as I'm going to the right, we're losing less. As I'm going to the right, I'm not growing that fast. I'm losing my growing ability. As I go away when I go to the right, as I come to the x-axis, we're decaying. We're losing. As I go to the right on the x-axis on the first one, I'm going away from it, so I'm growing. I can grow in a negative direction. Yeah.
It grows when it hits that, when it goes in the direction of x-axis.
As you go to the right, your graph goes away from the x-axis. The x-axis is this.
Right.
As it goes away from it, it's growth.
Oh.
We can have a negative growth, which is the bottom one. We can have a positive growth, which is the blue one. Okay, but the others, as they come and they converge to the x-axis, they meet the x-axis, that's decay. It's losing numbers. All right. So we already said the domain. The domain, as far as this class is concerned, is going to go from negative to positive infinity. Okay? Meaning I can plug in any value into our variable and we're going to get something out. We're not going to get an error. We're not going to get an undefined term. We're not going to get something that doesn't exist in the real numbers. Our domain exists there. Our range, I'm going to add one slight thing to this. I'm going to make it plus C. Okay? So our range, if we were talking about a graph that looked like this, we have this line here, which is y equals C. Okay, so that's why I added a C. So our range could start someplace. It could start someplace and go to infinity, or it could go from infinity and get to someplace. And it all depends. Now this could be a negative infinity here. We could have, so basically our graph will come very close to something called an asymptote. It's a horizontal asymptote. An asymptote is a line that you can't cross over in math or get to. Okay? But we'll build upon that concept a little bit. So let's graph these. So the parent function, we're going to call this. The reason I call that the parent function is that's the most basic base of 2 to the x I can get. So if I graph a few things, and we'll do this one in green, 0 or x, y, -2, -1, 0, 1, and 2. 5 points would probably be enough points to figure this out. Okay, careful. If I take -2 and plug it in for x, I get 2 raised to the -2. 2 raised to the -2 is 1 over 2 squared, right? Negative exponent wants to move locations, and 1 over 2 squared is 1/4. Then if I take -1, 2 to the -1, 2 to the -1 is the same thing as 1 over 2 to the first, which is 1/2. That should be a -1. If I plug 0 in, 2 to the 0 is 2 to a 0 exponent is 1. Whoa, where'd it go? 2 to the first? 2 to the first is 2. 2 to the second is 4. Okay, so let's see if we can graph this. I have -2, 1/4, it's like here. -1/2, it's up here. 0, 1 is here. 1, 2 is here. 2, 4 is up here. So notice this comes right along this line. It gets infinitely close to it. We'll never get to it nor cross it as I come out to the left. This is going to continue to grow forever and ever and ever. So now let's take a look at this one. So I have x and I have y. Alright, we're going to use the same values. Let's see what happens. Okay? So 2 to the negative 2 is 1 over 2 squared, which is 1/4. 1/4 times 4 is 1. Okay? Hey! Okay. So what's 2 to the negative 1? 2 to the negative 1. I'm circling it. 1/2. What's 4 times half? 2. What is 2 to the 0 power? 1. What is 1 times 4? What is 2 to the first power? 2. What is 2 times 4? What is 2 to the second power? 2 squared is? 4. 4 times 4 is? Okay. So negative 2 comma 1. Negative 1 comma 2. 0, 4. 1, 8. 2, 16. Using simple terms, your terms. What can you tell me about the difference between the purple versus green graph? Go simple. Doesn't have to be math related. What do you notice as I go to the right? Gets bigger, it's steeper, it grows faster. What do you notice to the left? It's going to be going the same thing. But this one grew fast. They both grew fast. They both grew exponentially. But one grows faster because I have a multiplier out front. So this one, the purple one, will grow at a rate 4 times as fast as the green one. Why is it 4 times as fast? Because it's times 4. If this was an 11, it would grow 11 times as fast. If this was a 6,000, it would grow 6,000 times as fast as our parent function. Was that okay terminology? This page requires add-ons that you don't have. Oh, okay. I don't know. Seems like I have everything there. Do you have everything on your sheet that I have on mine other than this page requires add-ons? Or does yours say that too? Oh, you must have the add-ons on your paper. All right, so graph 2 to the x and 1/2 2 to the x. Describe the domain and range of f and g. Okay. All right, 2 to the first, 1/2. 2 to the negative 2, 1/4. Or wait, 2 to the negative, right? 1/4. It's backwards. 2 to the 1.
Yeah, look, negative 1, negative 2, 0.
I did what?
Negative 2.
Oh! Oh, shoot. You guys are so smart, so observant. I love you guys. Negative 2, negative 1, 0. So I have 1/4, 1/2. Oh, you guys are awesome. All right. 1, 2 to the first, 2 to the second, 4. Okay, so this is the same one we graphed, right? So here, 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 here. So let's talk real quick. Of the green, what is it? What is the domain going to be on the green? Good. Okay. What is the domain got to be of the green? What's the domain of all these? I said negative to positive infinity. Good. Okay. Let's talk about the range of the green. Okay. So remember, the range is an elevator. So I said that this will never cross this line as I go this way. So if I'm on an elevator way down here, and I look out to the right or left side, do I see the graph yet? Tell me when I start seeing the graph being I'm at the very tip of the pen. Do I see it there? Or do I have to be slightly above it? the shadow. So right as I get up to there, so my range rounded bracket goes from 0 to infinity. Okay, it's a rounded bracket because I will not cross the x-axis. In the y direction, I won't cross the x-axis, which is 0. So I get real close to it. Okay, so now let's do this one in black. X and y. Let's see if we can figure this one out. There we go. Let's see if my dyslexia kicks in again. -2. Okay, we're good now. All right. 2 to the -2 is negative, or it's 1/4. What is 1/2 times 1/4? 1/8. Good. If I take -1, plug it in, 2 to the -1 is 1/2. 1/2 times 1/2 is 1/4. If I plug 0 in, 2 to the 0 is 1. Half times 1 is half. Plug 1 in, 2 to the first is 2. Half of 2 is, plug 2 in, 2 squared is
4.
half of 4 is. All right, let's see what happens here. So -2 1/8, that's just a smidge under there. -1/4 is here. There's half there. 1 here. 2 here. So is the black line growing faster or slower as I go to the right? Slower. Okay. What does it appear the domain would be on the black one? Well, they're all negative to positive infinity as far as domain in this class. What about the range? Is it still going to start at about 0 and go to infinity? So it'll go there a little slower, but it's still going to get there. So it's still going to go from 0 to infinity for a range. What's the difference between these graphs? The black one's growing at a rate half as fast as the green one. They'll both get to infinity as you go out to the right, but one's growing a little at half the speed. Why is it growing half the speed? Because I have a half out front. My multiplier is half. Where am I on this thing? May I move off this graph? Maybe this page requires more plugins that I don't have. Oh, good, I have all the plugins. All right. Now I have half to the x. Ooh, if I have half to the x, what happens if I plug a negative number in? Does it flip the fraction over? Okay, so let's do this one in red. I have x and I have y. -2, -1, 0, 1, and 2. Did I do that right? All right. If I take -2 and plug it in, it flips this over, so I get 2 squared, which is 4. If I plug -1 in, it flips this over, which gives me 2 to the first, which is 2. 1/2 raised to the 0 power. Anything raised to the 0 power is 1. 1/2 raised to the first power is 1/2. 1/2 raised to the second power is 1/4, because 1/2 times 1/2. So -2, 4, -1, 2, 0, 1, 1, 1/2, and 2, 1/4. What is this graph doing? It's decaying, right? The domain, negative to positive infinity. The range, it's coming from infinity and ending at 0. Rounded bracket because I won't cross over that. Anyone want to take a shot at what that 1/2 is, or that negative is going to do out front? So it would be all the same math, and my last thing would be multiplying by a negative, right? So that would be -4, -2, -1, -1, -2. Wait, is that right? Hang on. Oh wait, -0.5. Sorry, -1/4. Let's see what it is. I was looking at that when I didn't look there. So -0.5. Okay. So -4, -2, -4, 1, or -2, 1, -4, -1, -2, 0, -1. What did this graph just do? It flipped over the x-axis, didn't it? The domain is still what? -infinity, +infinity. While the range is what? Where is this coming from? Where is this coming from? It's going where? -infinity. So it came from -infinity and it's getting to 0. So notice how the range flip-flop. That should be a negative. So I have a negative and I have a positive. So depending upon where the graph came from in the y direction. Yeah.
So if the line hits the x-axis all in the area, it would become 0.
We're approaching it, yeah.
Okay.
It's decaying as we go to the right. Exactly right. Moving on. Okay, this graph represents a bacterial population, Y, after X days. Write an exponential function that represents the population. Find the population after 12 hours and 5 days. Oh. Okay. I think we can do this. Y equals A times B, and B is raised to the x power. That'll be our basic. We're not worrying about C right now. Where does it cross the y-axis? Where does it cross the y-axis? 0 what? 3. So where it's at 3 in the y direction. Okay, so let's use that. Let's go back to the beginning. Here. Where is it? Here. So remember we talked 0, A is our A value. So we're going to look at that here on our last graph. So what is my A value? Being that's where it crosses the y-axis. Great, good. So far I know y equals 3b to the x. Any idea how we can figure out what b is? Let me ask you this. So right now, does everyone feel comfortable that we are at y equals 3b to the x? How many unknowns are in that equation right now? I have y, I have b, and I have x. Do I have another location where I could find a b value or an xy value from our information? Do I have points that I know? Yeah. I know 112, I knew 248, I know 3192, and I know 4768. Doesn't matter which one I pick. I'll pick the 1, 12. 1 is x, 12 is y. Watch this, ready? What's b to the first? B? 12 equals 3b, yes? What's b equal to? 4. So my equation to this is y equals 3 times 4 raised to the x power. How many more slides I got? Okay. Yeah.
Did you divide 12 by the 3 to the 4?
Say that one more time.
12 by the 3 to the 4?
I don't multiply 3 and 4 together because 4 is raised to an exponent. Order of operations would say do the exponent first, then multiply. Don't multiply first, then get to the exponent. All right, so I think you have enough to get yourselves in some danger. So I'd like you to do page 2526. I will be marking this off next time. Woo! Fun stuff.